Section 250.30 Act 1 of the National Electrical Code addresses grounding electrode conductor connections for separately derived systems, such as those created by transformers. This section mandates that the grounding electrode conductor be connected to the equipment grounding terminal at the source of the separately derived system, or to the grounded conductor, typically the neutral, at the first disconnecting means. The first disconnecting means must be located within sight of the separately derived system source. Exception 250.24 further provides an alternative termination point, stating that the grounding electrode conductor may terminate at a metal enclosure that is considered effectively grounded according to stipulations in 250.24 ATWO 3 or 4. This exception introduces varying interpretations regarding acceptable termination points for the grounding electrode conductor in transformer installations. Let's examine the different perspectives on where to properly terminate the grounding electrode conductor in transformers. Firstly, there's the transformer's O-terminal or ground bus option. Proponents of this option argue that if the transformer is an integral part of the service equipment, it inherently meets the definition of a metal enclosure that is effectively grounded. Consequently, they believe the grounding electrode conductor can be appropriately terminated at either the O-terminal, which is the neutral point of the transformer's secondary winding, or the ground bus located within the transformer enclosure. Secondly, there's the neutral bus in the first disconnect option. This interpretation emphasizes that the code intends for the grounding electrode conductor to terminate at the neutral bus within the first disconnecting means. This is based on the understanding that the neutral bus represents the point where the grounded conductor is readily accessible and where the grounding connection is most effectively established. Thirdly, if the first disconnect lacks a neutral bus, the ground bus in the first disconnect is considered. In situations where the first disconnecting means does not incorporate a dedicated neutral bus, some argue that the grounding electrode conductor can be permissibly terminated at the ground bus instead. This viewpoint is predicated on the necessity of ensuring a robust grounding connection, even in the absence of a specific neutral termination point. My interpretation aligns with two primary termination points, the O-terminal at the transformer or the neutral bus in the first disconnect. When the transformer is regarded as an integral component of the service equipment, the exception outlined in 250.24 FR allows the grounding electrode conductor to terminate at the O-terminal. Conversely, if the transformer is not categorized as part of the service equipment, adherence to 250.30 ATWO necessitates that the grounding electrode conductor terminate at the neutral bus within the first disconnecting means. Several additional factors merit consideration during the grounding electrode conductor termination process. The main bonding jumper should be installed in accordance with 250.24 FR to establish a connection between the neutral bus and the equipment grounding terminal. This bonding jumper serves to equalize potential between the grounded conductor and the equipment grounding system, enhancing overall safety and performance. If the first disconnecting means consists of a circuit breaker, compliance with 250.12 ATWO mandates the inclusion of a ground fault protection device. The inclusion of a ground fault protection device mitigates the risk of electrical faults and ensures a prompt interruption of power in the event of a ground fault condition. In summary, the precise termination point for the grounding electrode conductor in transformer installations remains subject to interpretation and may vary based on the specific circumstances and local electrical codes. However, the two most commonly accepted options involve landing the grounding electrode conductor on the O-terminal at the transformer or landing it on the neutral bus in the first disconnect. It is imperative to consult with a qualified electrical professional to ascertain the optimal approach for each specific installation, taking into account all relevant factors and regulatory requirements. Now let's delve into some more detailed explanations to further clarify these concepts. The interpretation of 250.30 ATWO hinges on understanding the term separately derived system. A separately derived system is an electrical power source, such as a generator, transformer, or inverter, that has no direct electrical connection to the building's primary power source. The purpose of grounding a separately derived system is to limit voltage imposed by lightning, line surges, or unintentional contact with higher voltage lines and to stabilize the voltage to ground during normal operation. It also facilitates the operation of overcurrent protective devices in case of a ground fault. When a transformer is considered a separately derived system, 250.30 ATW dictates where the grounding electrode conductor should be connected. This connection is crucial for ensuring safety and proper operation of the electrical system. The language within sight in 250.30 ATW means that the disconnecting means must be visible from the separately derived system. This requirement ensures that anyone working on the transformer or the connected equipment can easily disconnect the power source. Exception 250.24 allows for an alternative grounding method under specific conditions. This exception is applicable when the metal enclosure housing the separately derived system is effectively grounded. Effectively grounded means that the enclosure is connected to a grounding electrode system that meets the requirements of 250.24 ATW 3 or 4. These sections outline the criteria for establishing a low impedance ground path that can safely carry fault current. The argument for terminating the grounding electrode conductor at the transformer's terminal or ground bus is based on the premise that the transformer enclosure is already effectively grounded. If the enclosure is properly connected to the building's grounding electrode system, it can serve as a suitable termination point for the grounding electrode conductor. This approach can simplify the grounding installation and reduce the length of the grounding electrode conductor. The argument for terminating the grounding electrode conductor at the neutral bus in the first disconnect is based on the principle of establishing a direct connection between the grounding electrode system and the grounded conductor of the separately derived system. This approach ensures that any ground fault current will have a clear path back to the source, facilitating the operation of overcurrent protective devices. The first disconnect is the first point where the power from the separately derived system can be isolated. This disconnect is typically a circuit breaker or a fused disconnect switch. The neutral bus in the first disconnect provides a convenient and accessible location for terminating the grounding electrode conductor. In cases where the first disconnect does not have a neutral bus, the ground bus can be used as an alternative termination point. However, it's important to ensure that the ground bus is properly connected to the building's grounding electrode system. The main bonding jumper plays a critical role in ensuring the effectiveness of the grounding system. The main bonding jumper is a conductor that connects the equipment grounding system to the grounded conductor neutral of the service equipment. This connection ensures that any fault current will have a low impedance path back to the source, facilitating the operation of overcurrent protective devices. The size of the main bonding jumper is determined by 250.28, which provides specific requirements based on the size of the service entrance conductors. A ground fault protection device is designed to detect and interrupt ground faults. A ground fault occurs when current flows through an unintended path to ground. Ground faults can be caused by insulation failures, accidental contact with grounded objects, or other types of equipment malfunctions. Ground fault protection devices are required by the NEC in certain applications to protect personnel and equipment from the hazards of ground faults. Section 250.12 ATW requires ground fault protection for separately derived systems under specific conditions. These conditions typically involve large capacity systems where the risk of a ground fault is high. It is imperative to carefully review the requirements of the NEC and consult with a qualified electrical professional to determine the appropriate grounding and bonding methods for each specific transformer installation. Understanding the nuances of 250.30 ATW and 250.24 FERA, as well as the various interpretations and considerations, is essential for ensuring the safety and reliability of electrical systems that incorporate transformers. The goal is always to provide a safe and effective grounding path that protects both people and equipment from electrical hazards. Also remember to abide by all applicable codes and regulations. Furthermore, when dealing with step-down transformers, which reduce voltage from a higher level to a lower level, the grounding considerations remain the same. The primary and secondary windings of the transformer are isolated from each other, creating a separately derived system on the secondary side. Therefore, the grounding requirements of 250.30 atW apply to the secondary side of the step-down transformer. Isolation transformers, on the other hand, are designed to provide electrical isolation between the primary and secondary windings. These transformers are often used to protect sensitive electronic equipment from noise and transients on the power line. The grounding requirements for isolation transformers are similar to those for step-down transformers. The secondary side of the isolation transformer is considered a separately derived system and must be grounded in accordance with 250.30 atW. It is essential to ensure that the grounding electrode conductor is properly sized and installed to provide a low impedance path to ground. The size of the grounding electrode conductor is determined by 250.66, which provides specific requirements based on the size of the ungrounded conductors. The grounding electrode conductor should be installed in a straight line and should be securely connected to the grounding electrode and the transformer enclosure or neutral bus. The grounding electrode should be a rod, pipe, or plate that is driven into the ground to provide a connection to earth. The grounding electrode should be located as close as possible to the transformer. In addition to the grounding electrode conductor, an equipment grounding conductor should also be installed to connect the metal parts of the transformer and the connected equipment to the grounding system. The equipment grounding conductor provides a path for fault current to flow back to the source, facilitating the operation of overcurrent protective devices. The size of the equipment grounding conductor is determined by 250.122, which provides specific requirements based on the size of the overcurrent protective device. Regular inspections and testing of the grounding system are essential to ensure its continued effectiveness. The grounding connections should be checked for corrosion and tightness. The resistance of the grounding electrode should be measured to ensure that it is within acceptable limits. Any problems with the grounding system should be corrected promptly to maintain the safety and reliability of the electrical system. In conclusion, the proper grounding of transformers is a critical aspect of electrical safety. Understanding the requirements of the NEC and following best practices for grounding and bonding can help to protect people and equipment from the hazards of electrical faults. Always consult with a qualified electrical professional to ensure that the grounding system is properly designed and installed. The grounding of transformers is essential for safety and reliable operation. Improper grounding can lead to electrical shock hazards, equipment damage, and fire. Always follow the requirements of the NEC and consult with a qualified electrical professional to ensure that the grounding system is properly designed and installed. This explanation provides a more comprehensive understanding of the various aspects of transformer grounding and the importance of adhering to the NEC requirements. By following these guidelines, you can ensure the safety and reliability of your electrical systems.